There are two types of ions, cations and anions. Metals form cations. Cations have a positive charge, while nonmetals form anions, which have a negative charge. The radii of an atom increases from right to left and going down the periodic table.
Cations tend to be smaller than the original atoms. Anions tend to be bigger than the original atoms. Look at the table for some examples.
This is Coulomb's law. The F in Coulomb's law is for the attractive force between two charged objects, ions for example. The K is a proportionality constant, or the Coulomb's law constant. The Q's are for the charges of object 1 and object 2, and then the distance is on the bottom, which is squared.
In Coulomb's law, distance is on the bottom of the equation. Because it's squared and on the bottom, it's inversely proportional, meaning that when distance increases, force decreases. This means that ionic compounds with smaller ions have a stronger force between them, making the bonds harder to break.
In Coulomb's law, charge is on the top of the equation, which means they are directly proportional. Ions with a greater magnitude of charge will have a larger attractive or repulsive force.
We are ions with small radii. It's hard to pull us apart.
Maybe we shouldn't have eaten all of those. Now we are ions with large radii. It's easier to pull us apart.
Water is a polar molecule, meaning that the electrons are not shared equally between the oxygen and hydrogen atoms. This results in a slightly negative oxygen portion of the atom and positive hydrogen end. Due to water's polarity, it is capable of dissolving many molecules and atoms into solution. This is a water molecule.
Water arranges itself so its positively charged ends are facing the negatively charged. Water arranges itself kind of like this.
This is sodium chloride, an ionic compound. Sodium is the blue atom and has a +1 charge. Chloride is green with a -1 charge.
We now add sodium chloride to water. The ionic bond splits and the negatively charged area of water is drawn to the sodium ion, while the positively charged ends of water are attracted to the chlorine. When dissolved in water, they should look like this.
For a compound to be soluble in water, the ion-dipole or dipole-dipole interactions between water and the solute have to be strong enough to break apart the bonds between the atoms. The energy released while breaking the bond has to be enough to overcome the interactions between the water molecules.
In Coulomb's law, the attractive force is equal to the constant, or Coulomb's constant, times the charge of ion 1 times the charge of ion 2 divided by the distance squared. Size and charge can affect the attractive force. As distance between the objects increases with size, the force between the objects decrease. As the charges of the object increase, so do the attractive force. Water is a universal solvent, and the magnitude of the forces between the ions in the ionic compound helps determine the solubility.